In my previous video, we saw what is binary search and how it works. We saw that how we can use binary search to find the position of an element in a given sorted array. In computer programming, you will encounter a lot of problems where binary search will be used, but we won't be finding the index of an element in a sorted array. There are a lot of ways and places where binary search can be applied, and that is what we're going to see in this video. So if you're new to binary search, I recommend you watch my previous video, What is Binary Search? I'll put a link in the description below. So let's get started. Previously, we saw only how to get the index of an element in a sorted array. Now, instead of using arrays, we will be using binary search on monotonic functions whose domain will be integers. A function is said to be monotonic if it is increasing or decreasing. So as x increases, y can either remain the same or increase. Something like this. So y is increasing, remains constant, increasing, but as you can see here, the y value never decreases. So this function is said to be monotonic. And we will be applying binary search on such functions, but we will be considering the domain for the function to be integers. So we will be taking only integral points and not the entire real line. Hence the name Discrete Binary Search. So the difference between discrete binary search and normal binary search is that in discrete binary search, we will be using function evaluation, and in normal binary search, we will be doing array lookups. So say we have a monotonic function f of x. Here we need to find the value of x for which f of x will be equal to some target value t. Previously, we were finding the target value in an array. Now we will be finding the target value inside the function and return its corresponding x value. So say over here our target value t lies somewhere over here. So our corresponding x value must be returned. So now let's see what sort of problems can be solved using discrete binary search and this idea of having monotonic functions. Now let me consider an example problem to better explain this concept of discrete binary search. You can pause the video here and read the problem that we are about to discuss. In this problem, we have n stalls. So here we have 7 stalls which are placed on a straight line having integral coordinates. We now need to place c cows in these stalls such that the minimum distance between the cows must be maximized. So say c is equal to 5. So say we place one cow here, one over here, one over here, here and here. So we have placed 5 cows over here. Note that stall can have only one cow in it. So here the minimum distance between cows is 2. Over here and over here. The distance between the cow at 3 and 1 is 2, and at 9 at 7 is 2. So we need to maximize this distance. This problem now needs to be solved using binary search, but we cannot solve it in the traditional array lookup manner since there is no array where an index is to be found for a target value. Instead, as the video suggests, we need to use discrete binary search. To do so, we need to first define a function f of x which is monotonic. If we can prove that this function is monotonic, then we can definitely apply binary search. So now let us define f of x. Our function will return either true or false, or we can say yes or no. It will return yes if for an x the minimum distance between the cows is at least x. So for any arrangement of cows, if the minimum distance exceeds x, then f of x will return yes, otherwise it will return no. So if we can denote the minimum distance as m, then x must be less than equal to m, and for no, x will be greater than m. If we consider this example and say x is equal to 1, for the given arrangement which we have drawn here, the minimum distance is 2. So we can see here that the minimum distance is greater than equal to x. 2 is greater than equal to 1. So f of x will return yes. So now we have defined f of x. Now we need to prove that f of x is monotonic. This function will be monotonic if there are a series of no's, after which there are a series of yes, or vice versa. First there is a series of yes and then there is a series of no. We can also consider this having a series of zeros and ones. So 0 0 0 0 followed by 1 1 1 1 1. If we can prove that a function follows this pattern, then we are good to go to use binary search. Let's take a particular value of x, say x1. So let's take x1 and assume that x1 returns yes. So what it means is that there exists an arrangement whose minimum distance is at least x1. Now for any x value less than x1, the function will obviously return yes, because the same distance m value will again be greater than equal to any value less than x1. So say for x1 it returns yes, then for any value before x1 it will return yes, yes, yes. On the contrary, say we have a value x2 which returns no, which means there does not exist any arrangement of cows whose minimum values is at least x2. So all of the arrangements have a minimum value which is less than x2. So for any x value which is greater than x2, the minimum value of any arrangement will again be less than x2. So x2 returns no. Any greater value will also return no. Our function is following a pattern of yes, 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 followed by no, 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 no. It is not following no, 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 yes, yes, yes. Instead, it is following yes, 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 no, 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 which is monotonic. If we choose this, the last yes as our x1, as we proved over here, all the x below this will be yes. And if we choose this no as our x2, then all the x's after this no will be no's. So essentially a problem boils down to finding the last yes in the function. We need to find the value of x which gives yes and which is the last yes in the sequence. That means x plus 1 should give no. So now let's take a step back and try to understand what we are actually doing. We need to find a monotonic function on a given problem. To do that, we find a function which returns a Boolean value, either true or a false. And then we need to prove that this true-false function is monotonic. That is, false are followed by trues or multiple trues are followed by multiple false. So any discrete binary search problem can be solved using this method. Find a function, convert it to yes or no's, and prove it is monotonic. Once proven, we can apply binary search. The constraints which are given in the problem were n is the range of 10 power 5 and the number of cows which is less than equal to n is also obviously in the range of 10 power 5. and this number line, the coordinates, so the value of x is in the range of 10 power 9. Now in a function we are binary searching upon x, so that will take log of x complexity, and in every iteration we are trying to find whether a possible combination is present which has minimum distance at least x, and that takes order of n. So our solution is n log x. For finding a combination whose minimum distance is at least x can be done using greedy approach. So what we can do is say our x is equal to 3. Since we're following a greedy approach, we place a first cow at the first stall. Now we go to the next stall and see if the distance between this stall and the previously placed cow is greater than or equal to x value. So the distance between this and this is 2. That means we cannot place a cow here. Next we come to 4. Now the distance becomes 3. So we can place a next cow at this position. Next, at this stall, again the distance is 3. So we can again place a cow over here. Next, at 9, the distance between this stall and the previous cow is 2. Since 2 is less than 3, meaning that minimum distance must be at least 3, we cannot place it over here. So we'll move on to the next position. We can place it over here. And again we can move to the next position, which is over here, and place it over here. So as you can see, we have formed a combination where our actual C value, the number of cows we're supposed to place, is 5. And the number of cows we are able to place is also 5. So our function will return yes. So at x equal to 3, our function will return x. And if you try to do the same thing for x equal to 4, it will return no. You will find no combination that will satisfy this condition. So for this problem, it is like at x equal to 1, at x equal to 1, it gives yes. At 2, it gives yes. At 3, it gives yes. Since it gives yes as 3, obviously at 2 and 1, it should too. And for 4, it will give no. And for any value greater than 4, it will only give no. So for evaluating the function f of x, that is checking whether a combination exists to satisfy the condition, it takes O of n. So therefore, our solution takes complexity n log x. So this is how you solve this question, and this is how you apply discrete binary search. In any other question, a very similar approach is being chosen. Always you convert your function into a series of yeses and nos and solve for x using binary search. If you would have noticed, there is something very interesting going on in this solution. We are brute forcing the answer to the solution. Yeah, you heard it right. We are brute forcing the answer. The x over here tells whether that the particular x is possible for the answer or not. If the function f of x returns no, that means no, that x is not the answer. And if it returns yes, it says it might be the answer, but we need the rightmost yes. So in this entire range of possible answers, we take the mid value, say 5, check whether the function gives true or false. Basically see whether 5 can be possible answer or not. If it is no, then we strike out the right hand side and go to the remaining left hand side, and again take the middle element and check if it is possible answer or not. And we keep doing this by reducing it half every time, and when we finally arrive at a single position where it is only yes, then we say that that is the answer and that is the rightmost yes possible. So in this manner you will find a lot of problems where we use discrete binary search, where essentially we are only brute forcing the answer, but we are brute forcing using binary search. So now let's look at the code for this and see how it's subtly different from ordinary binary search. So the code which is written over here is the binary search for the problem we'll be discussing till now, which has the function of this form: yeses followed by nos, and we need to find the value of x which corresponds to the last yes. So initially we will have left and right. Left will be set to 0 because the minimum possible answer to this question is 0, and right will be 10 power 9 as the maximum possible distance which is possible in this problem is 10 power 9 as given in the problem statement. As you can see here, the terminating condition is left less than right, and the mid is calculated as follows. We will see in a bit why we are having this terminating condition and why are we calculating mid like this. For now, let's see how do we move a left and right bounds for this problem. So f over here is the monotonic function that we're evaluating. So we're evaluating f of mid. If f of mid comes as true, then we're setting left is equal to mid. If f of mid comes as false, we're setting right is equal to mid minus 1. Let's say our left was pointing over here and right was pointing somewhere over here. Now mid say is somewhere, say let mid be equal to this yes. Now f of mid will give yes. So what we're doing, we're changing this L from this to mid. We are setting left as mid and not as mid plus 1, because if f of mid is true, that means mid could be a possible answer and that answer will lie somewhere on the right including the mid. So we are setting left is equal to mid, and say if our mid was say somewhere over here at no, so if f of mid gave no, that means our answer will be somewhere on the left hand side not including mid, because our answer has to be a yes. So we are setting right is equal to mid minus 1. Now coming back to why, we are setting mid as follows: left plus right minus left by 2 plus 1. In my previous video I said that we set mid as left plus right by 2, but if you observe carefully, this portion left plus right minus left by 2 is essentially left plus right by 2. Why are we converting left plus right by 2 to something like this? This is because if we do it this way, L plus R by 2, there could be an overflow problem. If left and right are very large integers, so adding two very large integers might give an integer which can overflow the integer range. Mid will lie between left and right. So even if left and right are very huge integers, mid will be somewhere between them. So if left and right do not overflow, so mid will also not overflow. But because we are adding left and right first to obtain mid, this addition can cause an overflow. That is the reason we convert left plus right by 2 to something like this: left plus right minus left by 2. You can see if you try simplifying this, you'll get this formula back. I suggest that you always use this formula for your code in the future whenever you write code for binary search. So now I'll tell you the reason why we are adding this plus 1 at mid. So say at one point our search space has only two elements. So left points here and right points here. And say the first element is yes and the second element also to be yes. Now if you calculate mid without adding 1, that would be left plus right by 2, which would give this element. So this would be mid. Now what will happen? F of mid will be true because yes over here. So now left will be equal to mid. So basically nothing is changed. Left is equal to mid. So again left is on the same position as it was previously, and it keeps doing the same thing, and so it will be stuck in an infinite loop. Instead what we can do, that since right is equal to mid minus 1, that means whenever we are updating right can never be the same as previous one. So we add 1 to mid, so that now mid, instead of pointing over here, it will point over here. So if this was an yes, then left will be equal to mid, so left will come over here. And if this was no, then right would be mid minus 1. That means right would become this first element. And we end up having the search space having only one element where left and right are equal. So we have to keep iterating in this binary search unless there is only one element. Once there is a single element, your answer will be that element, and that is stored in left. It is always stored in left. So that is the reason we are returning left. And since we have to stop when there's only one element left, a terminating condition would be that when left is equal to right. So we keep iterating until left is less than right. That means there are at least two elements in the search space. So here it is, guys. This is the code for discrete binary search, which is specific to this problem. Now, for a certain problem, you might need to find the first no, or you might have no's followed by yes. But the way you come up with the boundations, the mid value and the terminating condition is something similar. The approach you take is something similar. Always remember that whenever you set the boundary values, you always take into consideration of a case where there are only two elements, as I showed over here. Take two elements, check the conditions, and see if it is working or not. I hope you have understood discrete binary search and how you approach problems that require you to apply binary search. Please do not forget to like, share, and subscribe.